This is 7 or 6? 7? Let's give it 7. 7 or 6? I don't remember. No, I just want to write something so that they can check on the board it is clear or not. Anyway, so let's begin today's lecture. So last class we concluded by solving one problem using per unit method. So today I want to kind of revise that same thing, and also we will solve one more slightly difficult problem, but using the per unit method. So we'll just do the same thing but with more understanding today. Okay. So shall we quickly look at the question that we solved last time? So can someone explain me what was the question? So what did we have in that question? The last question which we solved using per unit system. Yeah. Okay. Okay. 1:5. Okay. Line. Is there a transmission line? What is next? Okay. Before this or after this? Okay. This one is connected on the transformer. One more bus and a transformer. Okay. Okay. It's connected to load. Okay. What more? So I can use call this as a line. What more data was given? Okay. Fast. What was the impedance? 1 plus 2j. Okay. 0.5 plus 1j. So what are the units for this? The unit was ohms and the unit here was also ohms. Okay, so that is very important. The unit was ohms. What about this? Okay, 0.5 plus 1j ohms, or you can write j1 ohms. What more data was given to you? S of what? S of the load, okay. How much? Okay, 30 plus 20. Okay. So this is, I can say 20J, and then I'll say kVA, kilovolt amperes. So when I call for this, I'll use kilowatts, and when I use for this, all right. So, all right, what was voltage here? 390 volts, 0 degrees. Okay. What more data was given? 400. Okay. Let me write the ratings in blue. So this is 400 volts. What was the rating of the line? Okay, 1600 kV or V. What was the rating of this transformer? What is 320? Here, this voltage. Okay. What else was given? Okay, so this was the data given in the last, in the problem that we just discussed in the last class. And what was the worry or what was the objective in this problem? So my objective in this problem was, given this load at this voltage, there will be some current, and that current will flow through the transformer, that current will flow through the line, that same current will flow through the other transformer and this generator. So there is always a lot of voltage drops in this path. So I wanted to find what was the voltage at the sending end. That was the main problem. Given the voltage at the receiving end, I want to find the voltage at the sending end. There is a reverse problem. Given the voltage at the sending end, what is the voltage at the receiving end? That is very difficult problem that we will see later. But now this problem, given this voltage, find this one, it is comparatively easy problem that we did last time. So how did we do that? If you don't use per unit system, then what you are dealing with is all these ohms and ratios and kilowatts and kVArs and all. So first you divide these two, you will get the current in amperes. Then you multiply this ohms into that amperes, you will get some voltage drop. And then you try to transfer the current from this side to the primary side, and then I think this was referred to the primary side, like, or this four side, this thing, and then you find the voltage drop, and then you again multiply that current with this. So each equipment, each component, you had to do one by one calculation. Only then you got the final answer. That was without using per unit. But if you use per unit system, what happens? This is your electrical, like, power system single line diagram. You understand all these symbols. From this you create another diagram. So another diagram is what? Reactance diagram. So what you have done is, this will become a voltage source, and then there is no impedance of this generator. It's a ideal voltage, at least for this problem. Then there is a reactance. This represents this transformer. Then there is a resistance and reactance. This represents this transmission line. Then there is another reactance. This represents this transformer. And then finally there is a RL. So this is the active power, and then this is the reactive power of the load. And then you just close this. So this voltage. This voltage is given 390, 0 degrees. So if I have all these values, I can find out this voltage very easily. It's a simple circuit solution. So there is no transformers in this. There is only one reactance of the transformer, which is like a approximate of the transformer. So the advantage here is that you can add all this X you can add, this R, this entire is one impedance, and then this is another impedance. You can just solve it more easily using this kind of structure. So wherever there are multiple voltage levels, so here the voltage is 400, here 1600, here 320, three different types of voltage levels you are seeing in this power system. So in order to solve the problem of having multiple voltage levels and all, we are using the per unit method. Okay. So now I want to just, I will not solve this problem again. This problem already solved last time. So I will just talk more about what is this per unit system before again starting another problem. Okay. So I just did a quick review of what we did last time. So the general formula is that PU, or per unit quantity. So this quantity may be anything. It may be per unit of impedance, per unit of voltage, per unit of current, per unit of power, or per unit of, in general, any quantity, per unit temperature, per unit speed, whatever you can define like that. Generally per unit quantity is, let's say, actual quantity, okay, divided by base quantity. So this is the general definition of what is a per unit quantity. So for example, if I decide that my base quantity, okay, is, let's say, 15 amperes, okay, so my base quantity is 15 amperes, so somehow I decided that, like that, okay, then every other amperes I can transform into per unit, like that. So let's say I have some I1 current is, let's say, 45 amperes, and then 70 or 75 amperes, and then 15 amperes, and then 1.5 amperes. So like this I have different currents. So I1, I2, I3, I4. So 4 different currents I am having. Now if I transfer all these 4 currents into per unit, what will be I1? I will write I1 PU. So I1 expressed in per unit. So that will be, so this 45 actual quantity divided by base quantity. So it will be 3 per unit. And there is no amperes here. So like that I just cancelled off amperes. Okay. Second one, I2 per unit. So 75 by 15, that will be 5 per unit. And then I3 per unit. So 15 by 15, 1 per unit. I4 per unit. So 0.1 per unit. So like this I can convert the amperes into per unit quantities. And we will solve the entire problem in this per unit system itself, and then the results that I get, I'll transfer it back to the actual base. So you can think of it like this. This is the actual units. So this could be amperes, volts, ohms, watts, or something like that. These are actual units. You transform into per unit and then do the calculation. So after your calculation is over, then again you get the results in per unit, then you transfer back to the actual unit. So this is the general steps. So I can say this is 1, and then 2, and then 3. 3 is this calculation, then 4, and then 5. So usually this is the procedure that we'll follow. So now I want to give more detail on this. I just give the examples. These are all real number examples. Like you can think of them as DC currents. But what happens in the case of AC? Suppose I have like this, my actual current, let's say I1 is 30 amperes, and then at the angle of 20 degrees. So if it's a complex number, so then what happens? So how will you express it in the form of a per unit system? So you do the same thing. So I1 per unit is nothing but, see, always this is a complex number, but this always denominator is a real number itself. There is no complex base. So you always take it as a real number. So simply 30 amps 20 degrees divided by 15 amps. You can consider it as 0 degrees, but amperes will cancel. So 15 will be 2. So then I will set 2 per unit at angle of 20 degrees. So I can always, 2 into cos 20 plus j 2 into sin 20. I can always do like that, but that is also in per units. Okay. So this thing you should again notice. This is actually quite useful for the power. Okay. Suppose I have, let's say, MVA base or KVA base or volt ampere base, something like that, S base. So let's say it is 10 kilovolt ampere. Suppose I have given something like this. My base power is 10 kilovolt ampere, and then some load is there. Let's say load is L1, which is given as 20 kilowatt plus J 15 kilowatt kVAR. Suppose this kind of load is given to me. Okay. Now I want to convert this load into per unit. That means I want to cancel kilowatt, I want to cancel kVAR, and so on. Okay. So in that case also you can do the same thing. So L1 in per unit system will be 20, and then this is kilowatt and then this is kVA, but doesn't matter. You can cancel. See, here kk is there, so that you should see the kilo and kilo. Sometimes if this is in just volt amperes and then the load is in kilowatts, then you have to multiply by 1000 and all that things. I am not telling about that. And then this could be even in MVA. So in that case, you have to be careful with that. So see, what is volt ampere? Is nothing but watts. So I can actually cancel this if you don't consider the complex and real, that kind of thing. So this number was 10. So this will be 2 times. The same 10 will apply for this also. It will be 1.5 times. So this also will get cancelled. kVAR also will get cancelled because kk is there, and then VAR or VA is similar if you don't worry about the real and complex part. So finally the answer will be 2 plus 1.5 J per unit. So this is my load. Okay. So to just quickly review, what I told is that per unit quantity is actual by base quantity. Base quantity is always a real number, and then the numerator could be a complex number also. And this is how you will deal with it. So now coming to, this was general. Now coming to actually only the power part. As I told last time, there are only 4 quantities that usually we convert to per unit system and all. So that is the S, and then the voltage, current and impedance. So these are the 4. So the base quantities we choose for only these 4. So I'll call them S base, voltage base, current base and impedance base, like this. So, and if I choose 2, the other 2 will get selected automatically because we have to follow the Ohm's law and all that. Okay. So for example, like normally the case is this will be chosen, this will be chosen, and then the other 2 will be, you have to calculate from that. So for example, if I choose these 2, first I will write down the expressions. So how do I express the current base in terms of S base and V base? So since I know like V into I is P, like think about DC quantities because this is only the base quantities, they are all real numbers. So these 2 is this V into I is S, therefore I is S by V. So simply current base will be S base by V base. So once I define these 2, I know IB also. And what is impedance base? So these 2 is this. So this is just simply the Ohm's law. Okay, I is R equal to V by I. So resistance is voltage by current, something like that. Now I can also do one thing. I can multiply V on numerator and denominator. So VB into VB, it will become V square. So V base square, and then IB into VB, it will become S base. Okay. So for finding the base impedance, I have either I can use this expression voltage base by current base, or I can use voltage base square by S base square. Okay. So shall we quickly do one example? So so let's say this is an example. S base is 20 MVA, and then V base is 11 kilovolts. Find I base and the other Z base or the impedance base. So what is I base? So S base by V base. So 20. I'll just put M VA divided by 11 K V. Okay. So VV will get cancelled. This K will be 1000 here. So 20,000 divided by 11. How much is that? How much is 20,000? Can someone quickly calculate it and tell? How much? 18.18. Okay. So this is in amperes. Okay. Always remember that the base will have a unit because volts got cancelled, kilo and mega we considered, only the amperes is remaining, that amperes will come here. Okay. Now if I have the actual current in a circuit and the actual current is 1000 amperes, then what I should do? So if I actual is 1000 amperes, so then I can now express it using this base. I can divide 1000 divided by this, so I will get some other number. that will be my I per unit. So I per unit will be 1000 amperes divided by 18.18 amperes. So amperes will cancel, and then I'll get some number. Okay, so that will be the current in per unit. Okay, so this is consistent with this chosen system of base. All right. So what is left to be done in this? I have to now find what is my Z base or the impedance base. So what is the impedance base? I can use this or I can use this, I will get the same result. So let's use this one. So what is V base? 11K V into 11K V, this one, divided by V square I have done, and then divided by S base, 20 MVA. Okay. So this is my Z base. Okay. So M and 2Ks will cancel out. Okay. So 11 into 11 is 121 divided by 20. Okay. And then I have 1V and 1V will cancel out. This is megavolt ampere. So there is V by A. 1 volt by 1 ampere is 1 ohm. So I will get the ohm. Okay. So nothing else. So here I can just 12.1 by 2. So 6.05 ohms. So this is my Z base. So like this you can calculate. So the moment you fix two values, the other two values are fixed. So this is this one and the other is that one. Okay, so this is quite useful or important one. So you can always, just for the calculation sake, you can say I want I base as 100 amperes and then I want G base as 5 ohms. Then what is the other two? So you can do all that calculations yourself. So I'm not going into that details. All right. So just now what I discussed is choosing the per unit system for one electrical problem. So now what happens? Suppose in the exam there is a question given. So one student chooses different like 20 and 11. Other student may choose 30 and 11, 30 MVA and 11. Then they both solve the problem. The in between solution like this part is all different because the base is chosen differently. But when finally the results are converted, both answers will match if they are correct. Okay. So the choice you have to do it in such a way that your amount of calculations will be lesser. So if you choose something like instead of 20 MVA you choose something like 18.6 MVA, due to some reason. So then every time you have to do the more calculations and all cancellations and these things, it will become difficult. So you have to choose your MVA in such a way that your calculations are faster and all. But then if you are using a computer program or anything, it doesn't even matter. You can whatever is it's same thing. All right. So now one more thing I want to talk about. This will be something called change of base. So because this per unit system is very, very advantageous, everybody follows per unit system for giving their data. So for example, there is a generator or there is a transformer, something like this. The manufacturer of the transformer will give the transformer parameters in the per unit system, not in the actual system. So for example, I'll take an example of transformer. Okay. A transformer is, its actual rating is, let's say 11 kV by, let's say 121 kV. This is the actual voltage rating. And actual impedance, sorry, the capacity, let's say it is 100 kVA. Okay. So this is the transformer. What I have given is, so voltage and then this one. These are the ratings. Okay. So voltage rating of primary, secondary, and then the MVA rating or the kVA rating of the transformer. These are the ratings. So what the transformer manufacturer will do, he will say that my ratings are nothing but my base quantities. So the ratings are equal to base. So like that they will consider. Okay. So in that case, what happens is here, let's say the X, let's say 0.1 per unit, okay, and then R is 0.02 per unit. So when you look at the data sheet of this transformer, the data sheet will show X value in 0.1 per unit and R value something like this. They will not give how many ohms, they will only give the per unit quantity. Okay. But for some reason, if you want to find out how many actually what is the resistance, what is the reactance, you have to consider that these ratings are nothing but the base quantity, and then you have to calculate the ohms. So can we do that quickly? So what is the Z base for this? Is S base, or sorry, V base square divided by S base. Just now we saw that. Okay, V by I, and then multiply V on numerator and denominator, you will get this. So what is V base square? So now the question is, for a transformer it is a bit tricky because there are two voltages. Which side you want to do? So this per unit reactance, whether you want to convert into ohms, refer to the primary side, or whether you want to convert into ohms, refer to the secondary side. You have to decide. So for now, let us convert this one into the refer to the primary side. So that is 11 kV. Then my V base will become 11 kV. So it will be 11K into 11K divided by 100 kVA. Okay, can I just do one thing? I'll just put this as 100 MVA so that my calculations are easy. Just for so now I can cancel this M and K. So kilo and mega get cancelled. So this is 11 into 11 is 121, and then divided by 100, that is 1.21. So 1.21 ohms is my impedance base. Okay. But what is the reactance of the transformer? You can per unit reactance. So Z per unit of the transformer is what? So 0.1 per unit plus J, sorry, this is 0.02 plus J 0.1, because this is X and this is R. So from this. So this one, if I multiply by, so how to convert from actual to base is divide by base. How to convert from base to actual is, or per unit to actual is multiply by base. So multiply into 1.21. So when I multiply these two, so first I'll do this. So it is 0.121 J. This is in ohms. And then what is the product of these two? 0.0242. This is also in ohms, this is also in ohms. So this is the actual impedance of the transformer in ohms. Refer to the primary side. So if you want to draw the circuit, you will draw something like this. This is ideal transformer. This is 11 kV, this is 121 kV, and then this one is 0.0242 ohms. So and then this one is 0.121 ohms. So like this you will draw the transformer, and then you can do your calculation in ohms. Okay. But then we said the ohms is not good. We have to calculate by per unit. That is more beneficial. So therefore, you can actually directly use these numbers and then do your calculation. Alright, so are you clear with this? Now the problem comes at one place. Suppose there is a generator which is having 80 MVA rating, and then it is 11 kV. And then the generator itself has some kind of a internal impedance. Okay, let's neglect the resistance of the generator. There is some reactance for the generator, which let's say it is 10%. Okay, so again, so here I say X is 0.1 per unit, or I will say X is 10%, both are same. I can express it as a percentage, or I can express it as a per unit. Okay. Now, imagine that this transformer is manufactured by one company, and this generator is manufactured by another company. For calculation of this 10%, the base used is 80 and 11 kV. Whereas for calculation of this 10%, the base used is 11 kV and 100 MVA. Whereas this is 80 MVA. So they are using different bases because everybody is manufacturing it. But then in my case, I purchase this generator and this transformer, and my circuit is like this. So, and then there is some load here. Okay, now I want to analyze this. So the problem is here, if I put 0.1 per unit, here if I put 0.1 per unit, these two are on different bases, and therefore your calculations will be wrong. So what you have to do now? So you have to assume one common per unit and then change everything to one common per unit. So which one will you select? See, luckily our 11 kV and 11 kV voltages are at least matching. So since this is 100, it's a round number. We can say 100 MVA I will choose for the entire problem. Then this will remain 0.1, whereas this 10% you have to change over to that one, and then you can put them in the circuit, and then you can do that. Okay. So I'll quickly derive how you can change. Okay. This thing. I'll just keep it like this. So this is change of base. So the problem is like this. Let's say impedance in per unit for base 1, okay, or I will say old base. So I have two systems. One is the old one, other is a new one. I want to transfer from old one to the new one. Okay. So this is known. Okay. So this is known. Impedance in per unit for a new base. This is unknown. So in our example, this is how much? This is 0.1, that is this one, 10%. And what is the base? 80 MVA and then 11 kV. Okay, so this was my old one. Now I want a new one. This is unknown. I don't know how much it is, but I know the new base for this one. So the new base is 100 MVA and then 11 kV. So this is my new base. This is 100. So I want to know what is this one. Okay. So how will I know? So just see what I am doing. Z base. So this is per unit, whereas this is base. Okay. Z base old is what we were doing sometime back. V base old square divided by S base old. Okay. This one. So this is the Z base in old basis. So and then this is new. So this is same new by S base new. So there is no confusion here. Now I'll divide these two. So if you divide these two, so I'll get something like this. Z base old divided by Z base new is equal to, so these two I'll say V base old by V base new, okay, whole square multiplied by S base new by S base old. Is that correct? So I just divided this by this. So this by this, old, new, and then new and old. Okay. So I just divided these two. So I got something like this. Okay. Now, what is this one? Z base per unit, Z per unit in old. Z per unit old is what? Z actual divided by Z base old. Okay. What is the other one? Z per unit new. What is that? Z actual divided by Z base new. Okay. Now if I divide this by this, or I want to divide, this will be in the numerator, this will be in the denominator. So these two will get cancelled. So I'll get something like this. I'll write here. So I'm writing this one. So Z per unit new divided by Z per unit old, so will be equal to what? So these two will get cancelled. New divided by old, so it will be what? Okay, Z base old divided by Z base new. Okay. Now in this place I can put this one. So these two are same. So these two are same. So therefore I'll just say equal to this one. V base old divided by V base new square into S base new divided by S base old. Okay, so this is my, now I'll say Z per unit new is equal to, I'll just take this one on the other side, Z per unit old. So this is my final formula. Is that okay? Let me verify. Yeah, correct. So it's nothing intellectual. It is just only manipulation of fractions and all. So given that calculation, I can now remove everything, and then we can actually, if somebody wants to quickly note down, you can. I'll just give you 1 minute. You can quickly write it down. I want to come back and then solve this box. What should be here? All right. I think I can remove this. So what I'll do is, this one I don't know. Okay. So Z per unit new equal to, what I'll do, I'll take the old one, which is 0.1, and then multiply by V base old by V base new. So in our case, we don't have a problem. 11 kV by 11 kV square. So k will get cancelled, 11 by 11 square. So that one we don't have to worry. Now I have to take S base new by S base old. Okay. So what is S base new? 100. So 100 by 80. So MVA both got cancelled. So 100 by 80. So this is my final. So this is all 1. So this is 100 by 80. I think this is 1.25. Is that correct? So this is per unit, or I can say 12.5%. Okay. So now when I solve the problem, what I will do, I'll take the generator and then I'll put the reactance of the generator, and then I'll say 0.125 per unit J. And then I can put the series, I'll put the transformer 0.1 per unit. So, and then entire thing is in 11 kV and then 100 MVA. So this is for the entire. So this step is very important for, this step is called change of base. Okay. So for doing the change of base, the right hand side, everything you should know. You should know what is my old voltage and new voltage base, and the old S base and new S base, and so on. So if you're not worried about deriving all these things in the exam and all these things, so just simply, if you remember this, you can solve any per unit kind of problem very easily, and you should have a calculator and all. Okay. So you can in fact you can actually write it down someplace, and then you can bring it, and then you can see it, and then you can solve the problem. Because as long as you have that formula correct, you will not have a problem. So the time is now 10:40. Okay. So in the second half of the class, we will again solve a similar problem, but in much larger size, and then we will see how all this things will help us. All right. So let's try one problem. So this problem is already there in one of the textbooks. So power system analysis. So so this is the textbook, and then the problem is example 3.7. Okay. So it's on page number 91. Anyway. So I'll start by making a drawing of the thing. So I just make a drawing like this. So this is the system. So there is one generator, and then there are two transformers, two transmission lines, again two transformers, and then one motor, and then one load. So let's give some labels. So let's call this G1, and then T1, T2. Sorry, this is T2, and then this is T3, and then this is T4. So this is M1, you can say, or M, and then this is L1, load. All right. So these are, and then the numbers for the buses. This is bus number 1, and then this is, there's one bus here, 2, bus number 3, bus number 4, bus number 5, bus number 6. So there are 6 buses in this system, bus bars or whatever. Now I'll give the data of the system. Data is something like this. G1, 90 MVA, and then 22 kV, and then 18%. So X is 18%. So what does this mean? So whoever has manufactured this generator, they manufactured the generator for the rating of 90 MVA with the voltage rating of 22 kilovolts, and their reactance is 18% or 0.18 per unit, taken on the base of what their ratings are. The actual ohms you can always calculate, no problem. So that is for G1. Now what is transformer T1? Transformer T1 is 50 MVA, and then it is 22 by 220 kV, and then it is 10%. So this is X, I'll put in the end. So the X is 10% for the transformer. So if you refer to the 22 kV side, you can calculate what is X in ohms, or 220 kV side you can calculate, right? So what is T2? So T2 is also, it's actually 40 MVA, and then it is 220 by 22 kV, and then it is 6%. So the reactance of this transformer T2 is 6%. Yeah, there is always resistance, but for this simplicity of calculation and all, they have neglected the resistance. But strictly speaking, you have to keep the resistance also. Suppose you are writing a software program to do the solution for this, you keep a variable R and then you keep the value 0. So some other problem comes where the resistance is given, you can always use the same program to calculate and so on. Next one. In fact, for the line there will be resistance. I will write that. So I'll just go a little fast. So T3 is 40 MVA, and then 22 by 110 kV, and then 6.4%, and then T4 is 40 MVA. This is 110 by 11 kV. Okay. Sorry, this is 11. Just take a note. This T2 is 11. All right. So T4 is 8%, and then the motor which is there is 66.5 MVA rating of motor at 10.45 kV voltage rating, and then its reactance is 18.5%. Right. So this is about the motor. So the load, so M1 and then L1. So the load is 57 MVA, and then 0.6 power factor, and then it has this is lag 10.45 kilovolts. Okay, so this is the parameters of the load. The total S is given, power factor is given, and then the voltage is given. So let's call this line 1 and then line 2. So line 1, a call. J okay, the ohms values are given directly. So this is the question. Actually, I did not tell the question. The question is like, you convert everything into a reactance diagram. So the question is like this. For the time being, forget about these parameters. If you look at this circuit, if I want to convert, this is a single line diagram power system. I want to convert it to a simple circuit. So what I will have? I'll have a voltage source representing this generator. Then I'll have a resistance or reactance. I'll have a reactance representing the reactance of this generator. Then I'll have two paths. This is transformer T1, line L1, transformer T2. Then this is transformer T3, line L2, transformer T4, and then there is a load. So the load can be something like this. This is my load, and then there is a motor. How do you model a motor? So motor is also something like this. Sorry. Motor is also a voltage source, but the current is going inside. So that means this is like a back EMF kind of voltage source. So you can model the motor in the form of a voltage source with a reactance. So all these things we have to put some numbers. Okay. So if you put some numbers, these things, then it is easy to solve this circuit. Whereas this circuit is difficult to solve. Okay. So there are no transformers here, just the transformer is replaced by a simple reactance. Right. So this is our problem now. We will not solve it. We will just transfer all these things into this, and then we will leave it there. So how to do this now? So the first step is choosing of base quantities. Okay. So usually in the question it will be given what is your overall base. Okay. Suppose it is not given. Look at all these things 90, 50, 40, 40. So these are all various values of MVA. You have to choose one MVA as your base for the entire power network. So usually we'll choose as a 100 MVA or 100 kV as the base. And almost 90 is almost equal to 100, so it is fine. You can actually take 90 also, not a problem. But since in this question they are given, so let me see what they are given. Alright, select a common base of 100 MVA and 22 kV on the generator side. Okay. So that's what is given. So my MVA is, I'll write it here, MVA base is 100. So this is the first of my base quantity. Let me use this color. So this is my MVA base, alright. There should be a kV base also. 2 I have to choose, the other 2 will get automatically selected. So it's also given in the question for generator G1, so you take 22 kV as the V base, alright. So whatever you choose for the generator, that will apply for this entire bus 1. Transformers your wish. You can put the transformer on the line 1 side, or you can put the transformer on the generator side. For our problem, let's keep this separate like this. So this is one region. So in this region, my voltage base is 22 kV, right? So what is the ratio of T1 transformer ratio? So if you look at T1, it is 22 kV by 220 kV. That means 10 times, isn't it? So whatever base you choose for generator G1, the base for line L1 will become 10 times of that. And I will also include the transformer T1 into that. Okay. So I'll just put a circle like this for this region and even T2. For this entire region, I will take V base as 220 kV. So I cannot choose this as I wish. This is all entirely determined by what? Determined by this turns ratio. Alright. Now at the T2 side, what is the ratio? 220 by 11. That means it is 1 is to 20. 20 is to 1 actually. So whatever is there, you divide by 20. So you will get how much? 11 kV. That 11 kV will apply for this all. So this is V base is 11 kV. So did you see how automatically choosing one voltage and following all the transformers, it will come like that. Suppose you choose 12 kV here, then 12 into 20 you have to choose 240 kV here. You have to, the whole idea is not to keep track of transformers. Just get it over with one place, so that here you don't have to worry about keeping track of ratios and all. So like that. So that is the shortcut in the using this. Now look at the line 2. So here you have to look, wherever there is a transformer, there will be a change in the region. So transformer T3, 220 by 110, 22 kV by 110, how much is the ratio? 1 is, okay. So therefore this entire region I will choose V base as 110. So this MVA base applies throughout the network, irrespective of the different transformer, different voltage level. But the V base will be different at different regions. So just a verification, is it coming proper? Like if T4 is there, what is the ratio of T4? 110 by 11 kV. Therefore, this 110 will become 11. So there is no problem in that case. All right. So all my equipments are covered in this. Okay. So all my equipments are covered. Then it is just application of this equation. You will get everything in this. All right. So let's do that. So look at this one. Okay. I want this one. So that is Z per unit in a new base. So what was my Z per unit in the old base? So I'll do the calculation for. So this is change of base for G1. So this one I want. So I'll put equal to. So what was the old one? So look at 0.18 multiplied by what is the old voltage and what is the new voltage. So the 22 kV what the manufacturer has used, 22 kV what we are using. So the voltage. So I'll just put 22 by 22 square, and then what was the S? It is 100 MVA, and what was the S base? It is 90 MVA. So if you do this calculation, you will get some number. So how much is that? Can someone quickly calculate? Point 0.2. So we got the answer 0.2 for this. 0.2 per unit. So I'll write 0.2 here. This is J.2 per unit. All right. Now talk about T1. So what is T1? So I'll put T1. Change of base. What was the old reactor T1? 0.1. What was the old voltage? So I am referring to the which side? I am referring to the second. So I will use 220 kV base voltage. So it is same. So 220 by 220 square. So this is okay. And what is MVA? So 100 by 52. So this is 0.2 again, isn't it? So 0.1 into 2, 0.2. So this is J.2. All right. This is also in per unit. Now let's look at the line. What is line L1? So here it is different. For the line, I am not doing change of base. I am actually calculating the base and then converting it into per unit. So what is the Z base for the line? So I'll write it like this. Z base line 1. What is it? I have to write V base square for the line 1 divided by S base for the entire system. What is V into 220 kV divided by 100 MVA. So M is cancelled 2 Ks, V is cancelled one of the V, V by A is ohms, and then this will be what? One will be 440 ohms. So I get the value 440 ohms. Oh, so if it is 100 MVA, then so that 480, 484. Okay. So I'll write it 484. Now what I should do? So here I got ohms, 48.4 ohms. So 48.4 divided by that one, ohms will get cancelled. I'll get per unit for the line 1. So how much is that? So that is the, actually the resistance is not given. So I can just make the resistance 0. So this is J 0.1 per unit. So what about the transformer T2? quickly. So T2 we need to do change of base. Okay. So for T2 what we are doing, and we have to use some of this place here. For T2 what I do, this is a colon. So old one is sorry 0.6 into 100 by 40. So this one is I think 220 square. So how much is this? 2.5 times of this. 0.15. So here J 0.15. So what about this one? T3. Transformer T3. So 110 and 110 the voltage problem is not there. Just 6.4 into 2.5 times. Isn't it? 6.4% into 40 MVA, 100 MVA, that ratio. How much? 0.16. All right. J 0.16 per unit. What about this line? We'll come to the line later. Just finish off the T4. 8 into 2.5 again. Because it's the same this thing. So 8 into 2.5 is 20. So 20%, which is 0.2. J 0.2 per unit. So these are all in per unit. Now look at the line. So what is the base for line 2? So I'll just calculate that. So V square is 110 square divided by 100 MVA. So kV square by so this is 1 ohms and 4 this by 121. So how much will be? What is that? 121. Is that 0.54? All right. So now we have finished this part. So come. So what will you do with the as a is
Sure.